Buongiorno a tutti. Good morning. Up. Yeah, so funziona. I'm Cyril Blondel, the Deputy Head of Mission here, and we didn't know it when we organized this event, but it happens to be exactly during the week between the departure of our previous ambassador on Sunday and the arrival of the new one on Monday. So this week I'm chargé d'affaires, incaricato d'affari, and it gives me the pleasure to welcome you here. So, Presidente del INFN, Monsieur le Directeur Général Délégué du CNRS, Egregio Sindaco, dear Director of the European Gravitational Observatory, dear member of the scientific communities, ladies and gentlemen. So welcome again to Palazzo Farnese. It's obviously a historic building. We just celebrated the 150th anniversary of the presence of the French embassy here, which is only actually a tiny part of the history of this grand building, and it's all the more obvious here in the Salone d'Ercole, which was designed by Michelangelo himself, which did a great architectural work, but maybe not so great in terms of heating arrangement, as you can see this morning, I'm afraid. But this palace is not only a witness to the past, but also a vibrant home for the future cooperation between France and Italy. And indeed, today we are looking beyond those Renaissance walls and towards the very edges of our universe. We are gathered to celebrate the dawn of a new era, the era of gravitational waves. 10 years ago, the scientific world was shaken by a discovery that forever changed our understanding of the cosmos by capturing the ripples in space-time caused by the collision of two black holes. The LIGO Virgo collaboration turned Einstein's 100-year-old theory into a tangible reality. For the first time, humanity did not just see the universe, we heard it. This revolution was the result of decades of persistence. At the heart of this success lies the Virgo detector. Virgo is more than a masterpiece of engineering. It is the fruit of a vision shared by France and Italy for more than 20 years. It is a concrete result of the exceptional synergy between the CNRS and the INFN. I'm particularly pleased to greet the director of LIGO and the mayor of Cascina. Your presence reminds us that such grand scientific endeavors require both a home and a heart. The territory of Cascina has become a global landmark for physics, a place where local roots meet universal exploration. I would like to extend my deepest gratitude to the INFN for organizing this prestigious morning. President Zoccoli, your leadership continues to foster an environment where high-level research can thrive. I would like to acknowledge and thank the Minister of University and Research, Anna Maria Bernini, who will be joining us a bit later to bring this event to a close with her intervention. Her support for the scientific dialogue between our two nations is deeply appreciated. I also want to warmly welcome the Deputy CEO for Science of the CNRS, Alain Schuhl, and the Director of CNRS Nuclear and Particle Physics, Christelle Roy. Your presence reaffirms the commitment of the French scientific community to this shared adventure. Most importantly, I want to salute the scientists and researchers here. You are the architects of the new astronomy. You remind us that human ingenuity, when fueled by cooperation, is limitless. As we look back on these 10 years, we also look toward the future of European research. The success of Virgo paves the way for the next generation of challenges, including the major European infrastructures Einstein telescope, which will ensure that our continent remains at the forefront of gravitational physics for decades to come. So, Palazzo Farnese and the French Embassy are proud to host this celebration. I wish you a very insightful morning. Look forward to continuing our discussion a bit later in the day over lunch. Grazie mille.
Thank you very much. Thank you. Can you hear me? Thank you very much to Minister Councillor Blondel for the address. It's now time to have 2 talks about the science that brought to the discovery and the meaning of this discovery. It's a pleasure to welcome Matteo Barsuglia, CNRS scientist, one of the leaders of the Virgo collaboration that made the discovery 10 years ago. Matteo, thank you.
Distinguished colleagues and guests, I'm here to tell you the first part of this centrally long story of creativity and perseverance that made possible the detection of gravitational waves. The story begins with Albert Einstein. Albert Einstein just having completed the so-called special relativity in 1905, a theory that unified space and time, matter and energy, Einstein started to address the problem of the gravitation. So why things are falling? It was an old question, a question addressed by Aristotle, by Galileo, Newton. And Einstein's great idea was that gravity is a curvature of space-time. Space-time is an elastic fabric. And in this figure that we see on the right, we see this 2-dimensional visualization of something that is very difficult to visualize because we live in a 3-dimensional world. And we see the Earth that turns around the sun because the space around the sun is curved. So the Earth takes the most natural path in a curved space. Of course, this idea is represented by equations. And for Einstein, it took almost 10 years to write down his famous field equation of general relativity, connecting matter, energy, and curvature. And looking at the Einstein notebooks, it's possible to follow and understand this wonderful intellectual journey. In 1916, manipulating his equations, Einstein found a solution, which is a wave, something that travels in space and carry energy. The gravitational waves, waves of space-time, ripples in space-time. Maxwell, one of the fathers of the electromagnetism, did the same in the second half of the 19th century. So manipulating the electromagnetic equations, he found a wave solution, demonstrating that light is an electromagnetic waves. Between 1916 and 1918, Einstein publishes 2 important papers about gravitational wave theory. So not only understanding that there are waves of gravity, waves of space-time, but also that those waves are produced by acceleration of masses. With a particular feature, the masses that accelerate should be asymmetric, so a perfect rotating sphere does not produce any gravitational wave. So in the figure, we see a perfect gravitational wave emitter, 2 massive bodies like black holes or neutron stars rotating around each other. After 1918, a desert crossing begins, a period full of doubts where physicists, including Einstein, don't understand if gravitational waves really exist, if they carry energy, if they can be measured. It's a period lasting for 40 years. Until 1957, there is a famous conference in North Carolina, the Chapel Hill Conference, where several experts in gravitation met And they arrived to the conclusion that the effect of the gravitational waves is to change the distance between free-falling bodies, like the circle of masses in the figure. And this effect can be measured. Contributors were Hermann Bondi and Felix Pirani that wrote important papers just after the conference. And after the conference, the effort to detect, to measure gravitational waves began in the early 60s. And the first to try was Joseph Weber, who in the University of Maryland built the so-called resonance bars, aluminum cylinders 2 meters long. So the gravitational wave crosses the bars and put the bars in resonance. And the idea of Weber was to detect the resonance with these detectors around the bar, with a piezoelectric detector around the bar. So despite a controversial claim, we think that Weber did not detect the gravitational waves, but he opened the way to this experimental research with several important ideas. One of them was taken then by LIGO and Virgo, the idea to build more than one detectors that work in coincidence, that can detect a signal at the same time. And also Weber inspired a whole generation of physicists, and in the picture on the right, I show Edoardo Amaldi and Guido Pizzella, the founder of the Italian effort, of the Italian School of Gravitational Wave Detection, with the cryogenic resonance bars at Frascati and CERN. So if Weber bars did not detect gravitational waves, they had the merit to start this experimental quest. But they had the problem. The Weber bars, they could detect a signal only at one frequency, at the resonance of the bar. It's like to hear a Beethoven symphony, but only be able to hear only one note. So we could not really understand the symphony in this way. And in the 60s has emerged the idea to use another method, to use an interferometer. So the idea was made by two Soviet physicists, and the idea was made to use this instrument built in the 19th centuries, and Michelson was granted by the Nobel Prize in 1906 by this invention. And the idea is the following. We have a light beam, and we separated the light beam in two parts. A gravitational wave crosses the interferometer and stretches the space in an asymmetric wave. So one arm gets longer, and the second gets shorter. And we can measure the delay between the two light beams as they recombine here. So in a technical term, they interfere, and so the power at the output of the detector changes. So measuring the change, this tiny change of power, we can detect a gravitational wave. It's a very simple idea, but the stretching of the space-time is very, very small. The gravitational waves, they stretches the space by 1/100000th of 1/10000000th of a meter over a few kilometers. So it's very difficult to measure this tiny effect over a forest of noise that can cover the measurement. In the 70s, there were two important events. The first was the construction of the first gravitational wave prototype in California, near Malibu. It was one of the Weber students, Forward, that constructed this first couple of meters detector, billions of times noisier than Virgo and LIGO, but also having the merit to start to understand the problems of these interferometric detectors. And on the East Coast, Ray Weiss, in this picture, MIT professor, started to address the problem of how to reduce the noises of a detector to detect astrophysical sources. And he wrote this document, 30 pages document, that really set the stage to build the kilometric detectors like LIGO and Virgo. So Ray Weiss, who passed away last year, inspired a whole generation of physicists, even in Europe, and he was awarded by the Nobel Prize in 2017 for these first ideas, because he was one of the father of LIGO, together with Kip Thorne and Barry Barish. So in this timeline, I show the story so far. So in yellow, the theory, in pink, the first experimental efforts and idea, but also in this box, some conditions very important for this story. First of all, the discovery of neutron stars and black holes, so emitters, potential emitters of gravitational waves, and also this astronomical observation in the 70s, the famous Hals and Taylor pulsar, where that a system whose orbital period decreases with time, and this observation demonstrates the existence of the gravitational wave. So it's this timeline already demonstrates that this story is a story of many conditions, so theory, technology, and also several other astronomical observations. Starting from the 70s, the quest for gravitational waves began in several groups. But let's focus on our own story. So Virgo history started with a meeting of Alain Brié, a CNRS based in Orsay, near Paris, and expert in lasers. Alain Brié already at that time made important contributions in verifying special relativity, together with John Hall, Nobel Prize in Physics, and Adalberto Giazzotto, INFN, based in Pisa, and expert in suspension system. So there was this link between good suspension system and good optics and laser that produced in 1989 the Virgo proposal. So Virgo was proposed in 1989 and was funded in 1994. So CNRS in 1993 and INFN in 1994. So the construction of Virgo started a few years later. We see here the central building on the Virgo side, and a few years later, the European Gravitational Observatory was funded. All those efforts led in the early 2000s to the construction of large interferometers. So LIGO in the west coast of US and east coast of US, GEO, a British-German observatory in Germany with a smaller arm length, and Virgo at the European Gravitational Observatory in Cascina near Pisa. And at that time, the commissioning, so the period between the end of the construction and the beginning of data taking started with the several years of collective work done by tens of people to reduce the noise, to understand the noise of these new detectors. In 2007, there was a major event. The Virgo and LIGO collaboration signed an agreement to exchange data, to share the analysis, to analyze the data jointly, and to publish jointly the results. So this memorandum of understanding transformed Virgo and LIGO in a single machine. So Virgo and LIGO, they detect the whole sky all the time, but alone they cannot understand the localization of the source. But together, by triangulation, they can detect, they can localize the source. So with this agreement, Virgo and LIGO were transformed in a single machine that work together. So 8 years after the first detection of gravitational waves, the community started to work together, and this is a fantastic and inspiring example of collaborative science. So today, Virgo and LIGO collaboration is extended to the Japanese project KAGRA. So there is this LIGO, Virgo, and KAGRA collaboration, and soon the community will become even more integrated. It will be called the International Gravitational Wave Network, a single scientific collaboration. So, but how are made these detectors? So they are microtron interferometer, able to detect a billionth of a meter of a distance of a few kilometers. But how this is possible? It is possible thanks to several technologies. We see here suspension systems able to reduce the seismic noise, super polished mirrors here that are made, those coatings are made in one of the key labs of the gravitational wave community at the Laboratoire des Matériaux Avancés in Lyon. High stabilized lasers and suspended benches, and of course, very large volume of high ultra vacuum system. So Virgo is the most large ultra high vacuum system in Europe with almost 7,000 cubic meter of vacuum. So detecting gravitational wave require to reduce all this noise. And just to give an example of the frontier of the research, we arrived really at the noise and intrinsic noise of the measurements. So when you have reduced all this noise, the minimum power change in the interferometer output that you want to measure is limited by the quantum vacuum fluctuation. So since the 80s, we know that quantum vacuum fluctuation can limit the interferometer, and it's the frontier of the limitation of the noise. So in this slide, I show all the progress in 50 years from the first prototype. In sensitivity, we gained more than 1 billion between the first prototype, the first detector, and the second generation detector operated in the 2080s. And thanks to all these efforts, in 2015, there was this first detection with this paper signed by LIGO and Virgo and signed by 1,000 persons, and Marica will detail more about that. And for Virgo, the story continued 2 years later with the first triple detection LIGO and Virgo. And this was a very important moment for us because, of course, for the first detection of Virgo, 14 of August 2017, but also because really we could start to localize precisely the event. You see here the region of the skies localized only with LIGO, and here the region of the sky localized also with Virgo. We could also started to measure new properties of the waves don't tested before, like the gravitational wave polarizations. So this is a complete timeline with theory, experimental efforts, and other conditions, technologies, development waveforms, where in France there was a lot of contributions by theorists, up to the triple detection and the BNS detection, the 17th of August 2017, that Marica will describe. So, and this story continue because we also have this new generation of brilliant physicists that we continue to upgrade these wonderful machines. Thank you.
Thank you very much, Matteo, for this very comprehensive introduction. It's a pleasure to call Marica Branchesi, Gran Sasso Science Institute, and also INFN researcher, a renowned expert in multi-messenger astronomy. Thank you, Marica.
So, distinguished authorities, distinguished guests, and distinguished colleagues, it's a pleasure today for me to tell you about this fantastic journey through the universe and through gravitational waves. So I go back to the first detection exactly 10 years ago, and I want to let you listen the sound that we were able to observe, to listen in Earth for the first time. This sound was extremely short, a fraction of a second, but told us a fantastic story. The story of two black holes, 30 solar mass each, that we saw the spiral of these two black holes and the formation of a new black hole. And to let you know how much are energetic these events, at the moment of the merger, the power emitted was larger than the power of all the stars in the observable universe. So there was a gravitational waves that propagates for 1.2 billion of years and reached the Earth exactly this 14th of September 2015. And this was incredible. The signal was really beautiful, was fantastic. At the beginning, the first hours, we were thinking, oh, this is an injection. Cannot be real, and was real. And it was fantastic. The signal was visible already in the raw data. It was also fantastic because it was a signal that told us for the first time that black hole live in a binary system, that black hole can merge in the Hubble time. And also there was a big surprise. The black hole was more massive than we expected. And this really changed our understanding of how massive stars die and how they can form black holes, and how two black holes can merge together and form a more massive black hole. Then there was another fantastic event in 2017, and this one was special already from the sound. But let me say a bit before what was this signal. So no black hole, but neutron star. What are neutron stars? Neutron stars are exotic stars. We have 2 suns in the diameter of Rome. This means that we have matter in extreme condition of density. So a teaspoon of neutron star is billion of tons. So we don't know the nature of matter at this density. And so now I let you listen again, another sound different from the last one, 1 minute. And then a flash in the gamma. So we immediately understood that we have something very special in front of us. So there was 1 minute, so 1 minute means neutron star, and then a gamma ray burst was detected by Fermi, confirmed immediately also by integral. And so we were putting together 2 messengers, light and gravitational waves. And what we were observing was the final dance of these 2 neutron stars, one around the other. When they are very close, they start to be disrupted. And so we have material around. We have the formation of these 2 jets that propagate almost at the speed of light. And then there are all this material around that is sub-relativistic, but sub-relativistic means 0.2, 0.3 speed of light. And we knew that there would have been the formation of light. So at that point started the observational campaign, more extensive in the human being. And I show you the region from where this signal was coming. Is the blue region. We knew the volume from where this signal was coming, and inside this volume there were 50 galaxies to be observed. At that point, all the instruments in Earth, all the satellites started to observe this region, And in one galaxy, at the same distance of the signal, we detected a new light that was not there before. These are all images taken during that days. So a light blue that in 10 days became red. So what we were observing was an object rapidly decaying in temperature, an emission that went from blue to red, and there is some absorption feature. This one were incredibly important because told us how heavy elements form in the universe. We didn't know before. And in the press, there was this message. So we saw the rainbow because we saw from blue to red. And one of the elements that you can form in this merger are gold. On the basis of the brightness and evolution of light, we know that there we form about 10 to 100 Earth in weight Earth of gold. The gold go in the interstellar medium, and from there you form new stars and planets. But this event was incredible, not only for the gold, but because show us how much is powerful to put together gravitational wave and lights. It was extremely important because it told us how are relativistic jet in this binary system merger. Told us how nucleosynthesis happens in the universe. We started to understand what is the nature of matter in this neutron star. And we started to say something about the rate of expansion of the universe, with big error now, but I will tell you a bit more later with it. And we started to make really tests of fundamental physics. So I want to underline how much these discoveries are important. These discoveries are collective discoveries. The paper on the multi-messenger signal that we detected was signed by 3,500 scientists all around the world, working together. This astronomy is very difficult. It's very difficult to detect the gravitational waves. It's very difficult to detect the electromagnetic counterpart. I think that this shows us how much it's important to work together, to work in collaboration. I think that diversity, inclusivity are extremely important. And if we want to overcome technological, scientific challenges, we need to work together. And now we are listening about binary black hole one every 2-3 days, and we have more than 300 signals detected in 10 years. I will tell the story about a few of them, but these are all the ones that we detected. So now you have to think, before the 15, we didn't know nothing. Now we know the mass of the black hole, the distribution of mass, how they spin, and we start to understand what is the formation channel of this black hole. This is one very interesting, because this one was the first evidence of existence of intermediate massive black hole. We start to see this 100 solar masses black hole. This is another one that was detected more recently. And I want to let you listen again another sound, again a new signal that we detected recently. This was the old one, the new one. This signal detected in 2025 was extremely similar in terms of black hole masses to the first one, but our detector were better in sensitivity, and the signal-to-noise ratio was much larger. And so for the first time, we were able to detect not only the signal from the two black holes merging, but also the sound of the remnant. And this was incredibly important for testing GR. So each new discovery really pushed the boundaries of knowledge and give us answer, but at the same time we have a richness of data that really open new mystery that we need to understand. This astronomy is really at the birth, because it's like when Galileo pointed the cannocchiale, so he started to observe the universe. But today we have the James Webb Telescope. This is a fantastic optical telescope. It is is a satellite, and this satellite is telling us about the first star, the first structure in the universe. And we want to do the same with gravitational waves. So we are thinking about the next generation, and we are thinking what we want in Europe. And what we want in Europe is Einstein telescope. So we have this underground infrastructure. We understudy there are two configurations, triangular shape and 2L. There are 3 site candidates, so EMR, Belgium, Netherlands, and Germany. Then we have the Sardinia site in Italy, and also now another site in Germany that is Saxony. And you know that recently there was an agreement between Italy, Sardinia, and Saxony to propose the 2L. So what means for the scientist ET? So ET will enable us to detect binary black hole up to the dark ages, so up to the early universe. And we will make population studies, so this means 10,000 of detection per year. So we will follow this binary black hole, binary neutron star along the cosmic history. And at the same time, close to us, we will have a precision to really understand how matter can exist in extreme conditions. So we want to solve a big mystery. For example, we have black hole coming from stars, and we have this gigantic black hole at the center of the galaxy. We don't know the connection among them, and with ET, we want to solve this. We are observing black hole coming from the death of star, but we think that there are black holes coming directly from the fluctuation of density of the universe, so the so-called primordial black hole, and ET will be able to detect them. So we have only one multi-messenger event, the one of the 17. With ET, we will detect 100 per year of these type of events. And ET is the perfect machine also to study the origin and the destiny of the universe. So let me say, this is my last slide, that I think that ET is really a big opportunity for Europe. We'll put Europe at the center of the exploration of the universe, and I think that through European collaboration, international cooperation, ET will become really a shared infrastructure for groundbreaking discovery, and will bring together Europe to push the boundaries of our knowledge. At the same time, it will foster, I think, the best value of Europe.
Thank you, Marica. And welcome to Minister Bernini, just arrived, so thank you very much. And now we move to running Virgo with the director of the LIGO European Gravitational Observatory, Massimo Carpinelli.
Authorities, colleagues, thank the Embassy of France to host this important event. It's proof of our long friendship and that will continue. So I am here to speak about a lot has been said about the gravitational waves. So I will concentrate on what it means having an infrastructure that can be used in the future for also in the past and in the future. Okay, so fundamental physics, I think, is a strategic asset. We have to understand that exploring nature, learning, try to learn what are the fundamental physics is important. If you are going to learn how the universe works, I mean, curiosity-driven science, this is a fundamental asset for society and also for technology. Large infrastructure of this type exists in the world. The most famous is CERN, of course, but gravitational wave laboratories can play the same role. The LIGO starts from a visionary Italian-French alliance, but also come specifically from a friendship of two great men, Adalberto Giazzotto and Alain. They built an interferometer to detect gravitational waves. We heard the history, but they really were the pioneer of this. They were able to convince all the funding agencies, CNRS and INFN, and the government to fund this incredible machine. And the history is a long history, like I said, 20 years of research, 20 years of work with politics to be sure that this kind of machine have been funded. You know, you cannot do fundamental physics without all the support of the government. So I still look to a forward alliance between France and Italy for the future of Einstein telescope. This is a very important point. So the international collaboration started, like I said, with two great countries, but then it was enlarged, and now we are 4 nations. Now Netherlands and Belgium joined recently. This is a picture that we took in Pisa last year, and Virgo collaboration is more than 1,000 members from 175 institutions, and we are part of a global network. So this is a beautiful picture of European Gravitational Observatory. LIGO is the only facility in Europe where gravitational waves can be observed, and this is the ideal place for testing the large R&D that are needed for the Einstein telescope. And in the past years, these sites has increased in number of people, number of interest, and number of technology that is being developed here. So I think that really having the honor to be the director of this, I can tell you that this, sometimes you feel that you really are doing something that is not easy, because there are so many people and so many technology that are here involved in this facility. I take just some pictures, some snapshot. So, for example, LIGO and Virgo, the Virgo interferometer is the largest volume of vacuum in Europe, even larger than CERN. And the super attenuator that have been developed by Adalberto Giazzotto are able to attenuate the seismic vibration by a factor of 10 to the 12. The chamber is hosting super attenuator that are hosted in the 3-kilometer long tunnel that you can see if you drive through close to Cascina, and they are able to achieve an incredible miracle, and this needs a lot of expertise: vacuum technician, electronics, precision mechanic, and physicists. They all have to work together to get the same results. Another important technology part are the mirrors. The mirrors are developed in LMA in Lyon, and that is the state-of-the-art laboratory. Even the American colleagues are produce the mirror here in LMA, which is as I said, the part of this technology that is needed to measure gravitational wave. They are suspended by fibers of glass fiber with the thickness of 0.4 millimeter. And they are an extremely advanced technique for building the power that is needed to measure the gravitational waves. So another point that I want to stress is that in the end, all this machine has to be shielded from
environmental noise, because all the noise that we have around, I mean, are, like was said, are able to just destroy the signal, which is very, very tiny. So we can be part of, we are able to see this just because we are able to shield the detector from all the environmental noise. And one important point, and I think also in this world is politically very important, is the fact that we can do the measurement that we do only because we are part of a global network. We are the first one to collect some signal coming from the world, from the space, and we then retransmit the alert to all other laboratories in the world. This is only possible because we are working like a whole community in the world. Last part, which is not, of course, the least important, is the fact that we are the place where we are training the next generation of physicists. We have seen that we have a lot of people, that this is a long history, and so if you want to be ready for the next generation, you really need younger people. And the training is the most important part, I think, that us as scientists have to do. So, you know, LIGO again is the place where the young generation can be trained and be ready for the Einstein telescope. So my final slides, I've been told that I had 10 minutes and I said my time, is that European leadership in this field is one that is very important. You know, Europe has been the beginning of these fields and has to continue being there, and we have to reinforce our collaboration. And this is only possible if we work together like a nation, like Europe, because I think that Europe should return to be the leadership in this field. And Italy and France have been the backbone of this alliance and will be also in the future. Thank you.
Thank you, Massimo. Next, two talks are from the representative of the two institutions that 30 years ago created and supported LIGO. We begin with Alain Schuhl, Deputy CEO of the CNRS. Thank you very much.
Thank you. Monsieur le ministre conseiller, Madame la ministre, dear Professor Zoccoli, dear Professor Ragazzoni, dear Professor Carpinelli, dear Mario Albetti, distinguished guests, ladies and gentlemen, it's a great honor for me to speak today at the Palais Farnese, a place that symbolizes the depth and continuity of the relationship between France and Italy. After the inspiring words we had just heard, allow me to take a step back and offer a perspective from a research organization that that has been involved in this adventure from its earliest days, and that remains deeply committed to its future. 10 years after the first detection of gravitational waves, we no longer see this achievement as a single event, but as the beginning of a long scientific transformation. Gravitational waves has become a new pillar of the observatory astronomy, reshaping the way we explore the universe and how we connect theory, experiment, and also technology. Virgo is a perfect illustration of a long-term European cooperation. It's not only an instrument, it is a result of decades of shared vision between France and Italy through the CNRS and INFN, supported by substantial public investment and a strong culture and scientific trust. Only few scientific projects demonstrate so clearly how patience, continuity, and cooperation can lead to discovery of global impact. As a deputy CEO in charge of science at the CNRS, I would like to emphasize how deeply this project reflects our institutional mission to support frontier science over the long term, to take risks, and to build durable partnership across borders. French and Italian teams have contributed at every level of Virgo, from theoretical modeling to experimental design, from advanced optics and material to data analysis and interpretation. The collective effort reached a decisive milestone in 2017 when Virgo joined the Global Detector Network, enabled the first precise localization of gravitational waves sources. Leading to the birth of multi-messenger astronomy, France and Italy in particular have made a decisive contribution to the emergence of this new field. Today, I would like to highlight the French contribution to this extraordinary adventure. From the early development of Virgo to the future of LISA and Einstein telescope, which will constitute major assets of European place France at the heart of 21st century multi-messenger astronomy. As early as in the 17th, France established itself a key player in the case of the gravitational waves. On the theoretical side, Thibaut Damour, a world-renowned physicist, made major contribution to the modeling of the waveform expected from the merger of impact objects, such as black holes and neutron stars. On the experimental side, Alain, a CNRS physicist, was one of the founding fathers of the Virgo project, together with Adalberto Gazzotto of INFN Pisa. Their pioneering work on laser interferometry made it possible to design instruments capable of measuring extraordinary small variation of the order of billions of a meter. This breakthrough is also the result of the collective effort of several hundred of physicists, engineers, and technicians working within CNRS, collaborating, and INFN partner university. It relies on the development of exceptional research infrastructure such as the Laboratoire des Matériaux Avancés in Lyon, where the more precise mirrors in the world are manufactured. In 2017, the Virgo interferometer joined the LIGO detectors, enabling precise localization of gravitational waves sources. This collaboration led to the observation of the merger of two neutron stars, marking the advance of multi-messenger astronomy and electromagnetic signal. French teams played a key role in the achievement by developing essential algorithms for signal analysis and sources characterization. But today, 10 years on, the most important message is not about what we have already achieved, it's about what lies ahead. Gravitational wave astronomy is still young. We are only beginning to explore its scientific potential, and the next generation of instruments will profoundly extend our reach. France is also a major actor in the future project and will take gravitational wave astronomy to entirely new horizons, the Einstein telescope and LISA. Expected to begin data taking around 2040, the Einstein telescope will be the most sensitive gravitational waves detector ever built. The CNRS and French laboratory, alongside our Italian, Dutch, Belgian, and Spanish partners, play a central role in the development of the key technology. The Einstein telescope will allow us to study the universe with unprecedented precision from the early moment after the Big Bang to the formation of evolution of galaxies. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the late 2030s, will open an entirely new frequency window from space, complementing ground-based observatories and enabling the study of phenomena such as merger of supermassive black hole and compact binary systems within our own galaxy. In this perspective, Europe has a unique responsibility and a unique opportunity. Together, France and Italy have played a central role in shaping the future alongside our European partners. Our laboratories are already deeply engaged in the development and the key technology, and our research organizations are fully committed to ensuring the scientific excellence and opening in the future infrastructure. Ladies and gentlemen, if gravitational waves teach us a lesson, is that profound discovery often requires time, sometimes decades, before their full impact become visible. They remind us of the importance of sustained commitment to fundamental research, even when immediate applications are not apparent. In this sense, the Franco-Italian cooperation embodied by Virgo is not only a scientific success, it's a model of truth between institutions, of continuity in public support, and of shared ambition at the European level. As a mark, this 10th anniversary, my message is therefore one of the confidence and responsibility. Confidence in our scientific community, whose creativity and excellence have already transformed our understanding of the universe, and responsibility as research institution and policy maker to ensure that the next generation of scientists has the tools, infrastructure, and international framework needed to continue this exploration. On behalf of the CNRS, I would like to reaffirm our strong commitment to working alongside Italy and our European partners to build this future together. Europe, united by science, has every reason to remain at the forefront of this extraordinary adventure.
Dr. Schuhl, and now it's the turn of INFN, President of the Italian Institute of Nuclear Physics, Antonio Zoccoli.
Thank you very much, colleagues, authorities, President Todd, and I think this is the proper place to say Madame Minister Bernini. It's a pleasure to be here and to celebrate the 10-year discovery of gravitational waves. If I have to think to the history in this field and to the Italian contribution, I have to start from the beginning, 4 centuries ago, with Galileo Galilei. Galileo is the father of physics, the father of mechanics, and all the history is starting at this point. And also this is a good moment to recall Galileo, because this was also the message that Nino Zichichi, who left us this week, was constantly providing us. Since that time, after 3 centuries, Albert Einstein, with the theory of general relativity, postulated the existence of gravitational waves. But, again, these were 2 great scientists, 2 single scientists, a visionary scientist. But it took 50 years to recognize that the times were mature to detect gravitational waves. And another visionary scientist, Edoardo Amaldi, one of the boys of Via Panisperna, the father of INFN, the father of CERN, the father of the European Space Agency, decided that the community, the scientists, has to open a new research field, the research field of gravitational waves. But at that time, it also recognized that in order to achieve this goal, it was necessary to develop a community. And he started to create the Italian community to detect gravitational waves. The first step was to try to detect gravitational waves with gravitational antennas, following the Weber ideas. But in these years, the community in Italy grew up, were becoming expert in the scientific field, and they were developing very advanced technologies. But in order to make the next step, we waited 30 years. At the end of the century, we had 2 more visionary scientists, Adalberto Giazzotto and Alain Brillet, that proposed a new way to detect gravitational waves through interferometer technologies. And at that time, we made another step. we recognized that it was not possible to have a local community to make this study, but it was needed an international community. And Italy and France joined their effort in order to achieve this goal. At the beginning of the year 2000, it was created EGO, it was built up Virgo, and it was started the search of gravitational waves. Again, it took 20 years to reach the goal. And through the Virgo detector, in 2015, the gravitational waves were detected. In 2016, we detected gravitational waves from the collapse of two neutron stars, and we opened a new era in the physics, the multi-messenger era with gravitational waves. In 2017, it was awarded the community, the scientists, for the Nobel Prize for the discovery of gravitational waves. So, it's a long story. Italy gave a very strong contribution on science, on technologies, on policy, pushing, building up an infrastructure in Italy to detect gravitational waves. Now we have achieved this goal, and now we have to look forward. We have to make the next step. And the next step is a third generation gravitational wave detector, is the Einstein telescope. Einstein telescope will open new window in the research, will help us to unveil the secret of the universe, to study the fundamental law of nature. But again, in order, and of course, as Italian community, we are proposing to host this important infrastructure in Italy in a different place, in Sardinia, which is the ideal place to host such an infrastructure. But again, now we need to make another step. We moved from single scientist to national community to an international community. But now, to reach this goal, I think we need to make another step, and we have to involve our government. So I hope that the governments in Europe, I know that the government in Italy is supporting this initiative, but we cannot do alone by Italy, and so I hope that the next two visionary people that will push forward this field will be our minister and the Minister of France, to have a joint effort to building up the new frontier infrastructure in this field, and to reach a fantastic goal and to push forward the frontier of knowledge in the next year. Thank you very much.
Thank you, Antonio. And now it's a pleasure to welcome the Minister of University of Research of Italy, Anna Maria Bernini, for a closing address.
Good morning, everyone. We are just back from Kenya, and we were told that saying good morning and Happy New Year from January to July brings good luck. So, good morning and Happy New Year to you all. That's true, isn't it? Antonio was with me. Monsieur le Président Antonio Zoccoli was with me. Ambassador Blondel, President of the Sardinia region, esteemed presidents of the National Research Institutes, distinguished member of the scientific community, ladies, gentlemen, friends. First and foremost, allow me to express my sincere gratitude to Ambassador Blondel for the kind hospitality in this beautiful palazzo, symbol of the spatial relation Italy and France hold since ever. Merci pour votre amitié, Monsieur l'Ambassadeur. And I would also like to thank Director General Alain Schuhl. Merci beaucoup à vous aussi. Merci d'être ici pour certifier l'importance de notre collaboration. You already said everything. You mentioned visions, hopes, opportunities. Let me summarize a few ideas and share with you some impressions and, again, opportunities to be shared. Because no one stands alone, as Antonio said before. We can't stand alone in front of the universe. This morning, as I said, you heard eloquent remarks delivered by outstanding scholars and scientists, both from Italy and France. You heard about the historic moment when, on September 14, 2015, gravitational waves were captured, and for the first time, the famous Einstein theory was eventually confirmed after 1 century of guessing. You heard about the importance of this very discovery that has changed forever the way we study astronomy, not only astronomy, cosmology, astrophysics, nuclear physics, and listen to the universe. That's fascinating and inspiring at once. I remember the surprise and the captivation generated by the two press conferences held at the same time 10 years ago, when the announcement was made. Now, 10 years after, 10 years later, let me tell you something more and equally extraordinary. Let me tell you about the value of our cooperation. What we celebrate today here is the outcome of a vision, of a common vision between our two countries and shared with other countries eventually. Dreams are a powerful propellant that fuel enthusiasm and hard work that make us achieve unheard goals. We cannot do it alone, as we said. We can't stand alone. We can't work alone. We can't research alone. We can't discover alone. France and Italy started working over 20 years ago together with a common goal in mind, and look at the results they got. By joining hands consistently every time, they've been able to change everything for everyone, as Professor Zoccoli, as President Zoccoli described, from Galileo Galilei to Einstein telescope, through visionaries of all times. 10 years ago, the LIGO and Virgo collaboration announced this fundamental scientific breakthrough through the foundation of Virgo and the European Gravitational Observatory by CNRS and INFN. It is therefore essential to properly celebrate the scientific success and to remember again the two founding fathers of the Virgo laboratory, Adalberto Giazzotto and Alain Priet, and to all those who believed in their vision from the very beginning. Today it is easy for us to be enthusiastic about the success of gravitational wave astronomy, to celebrate the rise of multi-messenger astrophysics, and to commit to further advancing this remarkable field. However, at the time of Virgo was conceived and built, the prevailing belief among scientists was that while Einstein had been correct in predicting gravitational waves, he had also been right in predicting that their experimental detection would be impossible. We did it differently together. The joint work of our two countries and scientists, through visionaries of their time, made much of the subsequent scientific and technological progress possible. France and Italy share the joint success, and we should regard it as an extraordinary example of what can be achieved when our two nations work closely together for years. But we are not here just to pat ourselves on the back, though. We have some ideas for our future, for our common future. The essence of celebrating this anniversary is to look forward. Europe proposes to construct the next generation gravitational wave observatory, the Einstein telescope, building upon our shared expertise and creating a state-of-the-art new laboratory on European soil. We think it is essential to do so if we want to keep being at the forefront of the international research in astrophysics. We believe that Italy and France can do it together, again. Italy has chosen to be proactive and has identified an optimal site in Sardinia, where a triangular-shaped facility could be built to maximize scientific returns. Our government has provided the necessary political and financial support for the realization of this research infrastructure at Sosenatos. The ongoing collaboration with Sardinia region is excellent, and I'm glad to see here, again, President Alessandra Todde. We've been working together for years. Thanks for your presence and thanks for your commitment, President, Madame le Président. In parallel, we are currently exploring the possibility of constructing the Einstein telescope across two distant European sites, one in Italy, in Sardinia, and one in Saxony, in Germany. The dual L, or the double L configuration, is strongly recommended by the international scientific community for its effectiveness and scientific power, making the Einstein telescope a truly European endeavor. Other options are also under consideration. What matters the most, though, is that the international community choose the best scientific solution ever, not a good enough solution. The best scientific solution ever. According to neutral, highly qualified scientists' opinion. The scientific community plays a fundamental role in the final choice of site and geometry for the Einstein telescope. Given its unbiased scientific interest and deep expertise in the field, we count on the support of French scientific community, and we are confident that France will choose the Italian proposal as the best option to fully realize ET's current scientific program and its future development, ensuring the infrastructure and operational lifespan exceeding 50 years. Our mutual collaboration over the years and its results speak for itself. To build the best possible Einstein telescope, we need an entire community coming together and polling their best results. French scientists, engineers, and technicians will be deeply involved in the project, strengthening the already outstanding collaboration begun with Virgo and Ego. Dear friends, chers amis, cari amici, by joining forces around the Einstein telescope, we reaffirm Europe's ability to shape its future through cooperation, science, and shared purposes. With this objective in mind, Italy and France share a common goal: reveal the secrets of the universe and the laws that govern it. You already said that. We reclaim for ourselves the chance to be visionary and to keep dreaming big, to keep dreaming big. Let us be bravest and let us build Einstein telescope together. Thank you.
So thank you very much to all. Lunch is served in the other room, and I think the event can be closed. Thank you.